Three, two, and one. Okay. Very good evening, everyone. So I'll be your host today, myself, Ujjwal Mishra. I'm a sophomore at Computer Science Engineering, and welcome to the session on multimodal autonomous AI agents. The session will be taken by Dr. Salakhutdinov. He has received his PhD degree from University of Toronto in 2009 under his advisor Jeffrey Hinton, where he worked on Boltzmann machine, which formed the basis of autoencoders later. After spending 2 years at his postdoc at MIT, he joined University of Toronto as an assistant professor in the Department of Computer Science and Department of Statistics. In 2016, he joined the machine learning department at CMU. He founded Perpetual Machines in 2015, which were later acquired by Apple in 2016. And then he served as the director of AI research at Apple, where also being a professor of computer science at Carnegie Mellon University. He's currently the vice president of Gen AI at Meta and board director Felix Smart. He's an action editor of journals of machine learning research, served on senior program committee of top tier machine learning conferences, included NIPS, ICLR, and ICML. Was a program co-chair for ICML in 2019 and journal chair for ICML 2024. He has co-authored and authored over 250 research papers, and his work has received over 200,000 citations according to Google Scholar. He is an Alfred P. Sloan Research Fellow, Microsoft Research Faculty Fellow, Canada Research Chair in Statistical Machine Learning, recipient of the Early Researcher Award, Kano New Researcher Award, Google Faculty Award, NVIDIA's Pioneer of AI Award, and is a Senior Fellow of the Canadian Institute for Advanced Research. He's a great researcher, a great teacher, and overall a great human being. I, on behalf of the entire IIIT UNA, welcome you, sir.
Thank you. Thank you very much. You can hear me, right? Everything is good.
Yes, everything.
Okay, great. So fantastic. So today I wanted to talk about some of the research that we've been doing over the last few years in the space of what we call multimodal autonomous AI agents. This is a very growing area of research, and this is what we see both big tech and a lot of work is being done in academia. So when we look at large language models, you're all familiar with large language models like ChatGPT and Llama and Gemini, and we sort of see a lot of interesting work happening in that space, right? Zero-shot ability of these models. You have very good, rich, strong representations from language. You can generate long and coherent text. These models carry some world knowledge, and you can also do a lot of interesting things like in context learning. But what we're going to talk about today is sort of what's the next evolution of these models, right? And it turns out that a lot of tasks that we perform today on a computer can potentially be automated, right? There is a lot of opportunity to automate some of kind of like simplistic tasks, or some of the routine sort of laborious tasks, and also augment human capabilities. So, for example, I give this example where, we at Carnegie Mellon University, sometimes my students try to set up AWS instance, right, for training these models. It's actually a pretty laborious process. The idea here is that can't I get my agent to go and do this work for me so that I don't have to do it? Or, for example, can I take papers that I'm going to discuss in this presentation and ask my agent, my AI agent, to go in and make slides so that I can present those papers, right? Or maybe, there's a lot of work now happening on the use of computer use, where, maybe my model can go and automate some of the tasks that I'm doing on Excel spreadsheets, right? Like do the analysis for me, build some models, extract information from the web, and sort of help me, build what I need to build. And today we're going to talk about what we call web agents, which is a general form of systems that actually can do interesting things on the web. So when we think about web agents, we think about HTML understanding, some form of textual representation, and then we also think about visual understanding. So, for example, I look at this web page, I have to understand what I'm seeing on this web page. And coupled together, we can do what we call web grounding, sort of understanding what we see on the web and trying to understand what we can click on and what actions we can take. And there is a lot of work. I'm not doing justice listing all of them. It's, started from 2022, all, or even from 2021 to sort of all the way to today. Here's one example, right? Just to give you what these systems can potentially do. Let's say I give you a task: navigate me to a good page, to a page of a good Thai restaurant in Pittsburgh. It should have at least 200 reviews and 4.5 stars, and give me the one with the highest rating, right? So let's say I give that task to my agent, right? And this is what my agent can do. It's a cherry-picked agent, right? It goes on Yelp. It starts searching in Pittsburgh, tries to look for Thai restaurants. And you see on the right-hand side, the agent is thinking, it generates chains of thoughts, it's trying to reason what it needs to do. It scrolls down and eventually basically finds the restaurant called Pusadi Garden, which is a pretty good restaurant, pretty good Thai restaurant, right? Or I can say, hey, make a reservation in Pusadi Garden for 2 people at the earliest day. Use my name, JY, and a phone number. And so the agent goes to Google, finds this particular restaurant, finds the available date, and says it's for tomorrow, and actually makes a reservation for 2 people, and has the phone number. So it's trying to type in the phone number, and then stops because I need to get a confirmation, right? So it stops. It basically saying, I need to get the next action is stop and able to proceed without confirmation code, right? So what you're observing here is agents that fully autonomously going on the web, finding the right piece, what they need to do, and sort of to make a reservation. Or maybe another fun example, I can say, help me navigate to a shirt that has this on it, right? And so I have to understand what this image is. I go to Amazon, I finding looking shirt. This is the dog shirt, so it has dog. And then I kind of like searching through like what kind of shirts, and actually, there is a shirt like this that's Amazon is selling, right? And it sort of found that shirt. Now, one caveat with all of these examples right now is that these are heavily cherry-picked examples. That means that we kind of like out of 20 runs, I think 1 run succeeded, and we're kind of like showing what these models can do. Okay, so today I'm going to talk about 3 things. I'm going to talk about Visual Web Arena, which is the work that we've done at Carnegie Mellon University for a way for us to evaluate multimodal agents. I'm going to talk about research for large models. You can think of this as a test time inference for building these style of models, so we're actually doing inference in these models. And then the last part, I'll talk about how can we build internet scale training data for these agents. So it's sort of like trying to go on the web and really trying to get a large training set, synthetic training set, so that we can actually improve those agents. Okay. So let's start it with Visual Web Arena. There is an environment called Web Arena, which was built at CMU. Beautiful environment. It's probably one of the most realistic web environments at the moment. It has websites from popular categories like shopping, Reddit, GitLab. It's self-hosted. It's open sourced. The data that comes to these environments is actually coming from real websites like Amazon, Reddit, and GitHub. And what's interesting is that humans can solve about 78% of the tasks, but it's difficult for language models. Language models, state-of-the-art language model can maybe solve about 14% of the tasks. However, tasks are fairly messy because you have to deal with HTML, and dealing with HTML is actually pretty hard. There is a lot of JavaScript, CSS code, you're moving objects around the web page. Context length can potentially increase significantly. So you sort of have to deal with this. Right, and so kind of like dealing with, again, HTML is pretty hard, and actually building just based on the text alone, we believe is just insufficient. So we again, with the Web Arena folks, like these are PhD students at CMU, we've built to track the process of multimodal agents. So we've designed some of these what we call visually grounded tasks to test the ability of these agents. So you have visual inputs, you have potential visual outputs that allow for interesting, realistic sort of environments. And we've looked at 3 domains. One is the shopping domain, what we call one-stop shop. One is a Reddit domain, sort of like questions and doing something on Reddit. And the other one, OS class, you can think of it as a Craigslist, right, where you can sort of make a posting, search for certain items that you want to buy. right? So for example, here's the task, and I can tell, buy me the cheapest color printer and send it to Emily's place as shown in the image. I take a picture of, the address, and that's the task. Let me show you what these examples are like. Again, these are completely simulations, right? It's a simulated environment. You fully control what the environment does. But let's say I give you a picture of this bike and say, hey, find me the exact bike that's listed for, somewhere between $300 to $500, and make a comment offering $10 less than the asking price. Okay. So what the agent needs to do, the agent needs to kind of like find the bikes category, fill in the form, search through, find this particular bike, right? That's the bike, and then make an offer, and offer $10 less than the asking price. Right. So I'm asking, hey, would you consider $385, right? And the person is selling it for $395, for example, right? And so this is just one example of agent executing your task that you're giving it, and sort of crawling, going on the web, finding the right information, and completing it. Here's another example. I've shown you this, buy me the cheapest color printer and send it to Emily's place as shown in the image. And you can see the image is actually upside down. So we made it specifically difficult for visual kind of like recognition systems to be able to say, okay, actually what I need to do is I need to turn it 180 degrees to actually find out what the address is. And so what the agent needs to do, it sort of needs to crawl, it needs to search by price, it needs to sort of find the printer, it needs to add to the cart, then it has to fill in the form with the right address, right? It's all has to be done autonomously. All right. And then, you basically place an order. Right. So here you basically completed the purchase. Again, because this is done in a simulation, we can actually test the ability of these agents to do these kinds of tasks. Here's an interesting one. I can ask, what is the 2022 total nominal GDP of the area that produced most sugarcane in the billions of years, right? And sort of like you have to understand this graph. And there is a sugarcane produced in all Asia versus Brazil, I believe. And I think in 2022, it just so happened that Asia produced more sugarcane than Brazil. And so what the agent needs to do, it needs to understand this graph, it needs to understand the plots, and then has to go to Wikipedia and actually find the GDP of Asia in 2022, right? So it visually has to understand the graphics, it has to find the right information and then extract the right information, right? Now, the way that these environments are set up is they set up through what we call partial observable Markov decision processes, or Markov decision processes, MDPs. So you have definitions of what that means. So you have a sequence of observations. Observations could be images, could be HTML, or could be what we call accessibility tree, which is kind of like a simplified representation of HTML, right? Where you're associating which element on the web page with a specific unique ID. So you have an observation, you have set of actions that the agent can take, and these sets of actions are actually pretty diverse, right? They both discrete and continuous. So for example, you can click on a particular element on the web page, you can hover over a particular element, you can type in a particular element, and you have to specify what you need to type. So for example, if you're searching for something, or if you're filling in the information, you can say, well, in element ID 18, type this information, right? You can create a new tab, you can focus on the tab, you can close, you can go to a specific URL, you can go forward, go back, you can scroll up and down, and then stop basically means that you found what you're looking for, or you've completed the task. So stop typically says, okay, my action is I'm stopping to, because either I've solved the task or because I'm done. You have what we call deterministic transitions. So given the state, right, internal state of the environment, and given the action, you get the next state. And the way you're generating observations is that given the state, there is a way to generate the observation, right? So what we do is that there's internal state of the simulator. And once given the state, we can actually generate the HTML. We can render the web page, right? So anytime you click on, or you take any action, you always go to the new state, and that's from the new state we generate an observation, right? So generating
Sir,
observation. Yep.
over here, Mr. Aditya is asking, like the state to action, that space has like it would grow multifold with each step
Yes,
that I would take. So how
that's
is that
exactly right.
managed? Like with that would be a huge space at the end. So that. Doesn't make
So the
any
way,
sense.
yes. So that space, that space. Let me show you what that means. It's like, given a particular state, right? Let's say the state. You have a web page, and you take any particular action. Any of these actions, right? Can once you take an action, you go to the next state. But the space itself of, if you look at the space itself of all the states, it's pretty large, right? It's the whole
Yeah.
simulation, whatever we have in the environment, right? So the state is actually pretty large because there's all kinds of data. There's all kinds, I think, and so it's kind of like taking any action. And in our case, any action you take will lead you to the next state, right? So the state space is actually pretty diverse, and it's pretty big. And so we have to build models that can navigate that space and solve the problems, and that's where the challenge comes in. And we also have a reward function. You can think of reward function right now. It's a reward function that basically tell us, have we solved the problem or not, right? Have I placed the order? Have I filled all the information correctly? And because it's a simulation, we know exactly whether you've accomplished the task or not. So we have kind of, I'll talk about what the reward function is. But let me show you what that means. For the agent to do these complex tasks, right? So, for example, if I say, buy me the cheapest color printer, the perfect agent, would actually start on the home page, right? Navigate to the printers category. So you have to click that. You have to take an action. Then you have to sort by descending order in price. So you kind of have to figure out which one has the cheapest one, right? Then you have to click on the cheapest printer. So again, each action you take has to be very precise, because otherwise there is a lot of actions you can take on this web page. So you really have to understand visually, and you have to understand what to click on. Then you have to add it to the shopping list. Then you have to proceed to the checkout. Then you have to fill in the form, right? And so like each one of these actions is actually a fairly complex action, like filling the form with the information provided to you in the image. And then you have to place an order. So the important thing I want to make here is that, unlike in models like you're probably familiar with ChatGPT, where I give you the question, you give me the answer. Here, the difference is I give you the task. I tell you, do this for me. And the agent actually has to go and execute a sequence of actions,
Ah,
right? In order to accomplish the task. It's no longer question answer. It's more like, I give you the task, and then you go and you accomplish this task.
it's more like training a robot in to walk in virtual environment.
Exactly. Exactly. It's like training a robot by, taking actions and understanding and be able to execute autonomously those actions.
Yes.
That's exactly right. So when we looked at this particular environment, the distribution of tasks by difficulty, we basically, you see like there's a shopping environment, there is class field is like more like Craigslist environment where I'm trying to, maybe like have posts and listings, and I have Reddit type of environment. What's interesting here is about 15% of the tasks, what we call easy, both in terms of visual difficulty and in terms of reasoning. It basically means that you only need to do you need to take a few actions, maybe 2-3 actions, and you can solve the task. And visually, like, it's very clear what we're trying to do. But quite a few tasks have both a visual difficulty and hard. And the way we measure this is we basically ask students to solve these tasks. And reasoning difficulty, we basically measure it. If you have to take a lot of steps to accomplish the task, we consider it to be kind of like reasoning difficulty. And visual difficulty, the students would rate for us, like, yeah, this is like much harder, because I really have to understand, like the sugarcane example, I really have to understand, I have to look at the graph and have to figure out, like, in 2022, was the sugarcane, who produced more sugarcane? And so you have to do a little bit of visual analysis in order to understand what the task is. Right? So there's like distribution of tasks. We have about 1,000 tasks here, and that's the distribution of easy versus difficult. Right?
Okay.
Now, and then the way that we're evaluating these models, right, is to say there are certain times where we have exact match. Right? For example, I can say, what's the IC number of the company that occupies the largest portion of Warren Buffett portfolio, right? And so there is one specific company, I can't remember what it is, I think it's Apple, and they have to find the ISIN number, right? And so you kind of
Yeah.
have to, provide. There's sort of visual, what we call verifiers. So for example, if I show you this image and I say, add something like what this man is wearing to my wish list, right? And so then we're measuring in the wish list, is this a polo shirt? Because it's a polo shirt. Is this a green shirt? And we kind of like have these visual question answering verifiers that at least give us some proxy way of saying, did you find the right information or not, right? Or like if you're navigating to the listing, you can have like, hey, it has to be, between 2,500 to 25,000, but it has to exclude 30,000, from to 30,000, right? So we basically have a way of verifying, have you sort of solved the task or not. Now, when I look at large language model agents, or what we call visual language model agents, because they have to understand visual information as well. When we think about visual language model, we can use HTML, right? It's kind of like a long representation of what we see on the web page. It's very cluttered. There's a lot of information. There's a lot of confusing information. We also have been using what we call set of marks representation, which basically puts bounding boxes around clickable elements. So elements on which you can click on, you put bounding boxes around, and then you associate unique ID with each clickable element. And then the model has to sort of like say, okay, click element ID 35. And the way that, these models operate is that you have an original web page, right? You then put set of marks representation, and then you're giving set of marks elements as a text context. You can say, okay, element 7 has like description. It's a picture of the pumpkin. Element ID A is, has something else. So kind of like label every single element. And then you go to the visual language model, and the visual language model, given this information, tells you what action it needs to take next, right? So more specifically, let's say I have this goal. I'm trying to find this post on Reddit, navigate to the comment section of it. Like somebody posted the sushi. I want to find, get me to the comment section, right? So I have an observation. I start on the Reddit. I have some description. And then it's associated with set of marks. And then it goes to the multimodal large language model. And the multimodal large language model says, okay, let's think step by step. The objective is to navigate, to find the post and navigate to the comment section for it. From the observation, I can see to navigate to this listing, I need to click on the comment link associated with the sushi. In summary, the next action I will perform is click element ID 34. And ID 34 will take me to the sushi kind of like thread. Right? And so this is what like a single step of the visual language model would look like, right? So you have some kind of chain of thought. The model reasons what it needs to do, and then it has to take an action. Right, and the action here, just the action, click on specific element, and then you go to the next. State. What's interesting here is that when we've looked at performance of these agents, right, we sort of look at text. We look at text and We look at text and captions. We look at multimodal. Performance improves. We look at multimodal plus set of marks. Performance slightly improves. So you can kind of like see if you have visual information, performance improves. But if you look at human performance, as humans being able to solve these tasks, the performance is way higher, right? And it's interesting because, like when we look at, something that's a little bit more precise, when we look at accessibility tree, caption generation, when we look at multimodal model, set of marks, again, the best performance at the time was 16%. I think right now we can probably hit 20% with our best models. On these kinds of tasks, humans can hit, close to 90%, right? So that's interesting. And so here's one example. For example, it's a cherry-picked example where GPT-4V at a time was able to solve the task. So for example, I tell it, hey, I don't like the author of this image from one of the hot posts on F memes. Can you help me block them? So they put some image. You say, I don't like this image. Help me block the user who posted this image, right? And so the agent has to start on the home page, has to search for this particular, subreddit thread, navigate to the listing of all forums, navigate to this forum, find the user who put, who posted this image, click on button, and then basically confirm blocking that particular user. Right. So that's just an example of a series of actions that the agent need to do in order to help you block the user. But the important thing I want to make here is that the agent has to really understand both visual information, text information, and also what the user is asking, which also has visual information. right? And so when we think about these settings like Visual Web Arena, it's a step towards building more general purpose agents. Of course, the tasks are not very consequential. At this point, they don't represent significant economic values. The tasks are simpler right now because a lot of these tasks students at CMU designed.
Yes.
Um, and current LLM agents do not even do well on those tasks, right? And the long-term goal is to automate productive, economically valuable tasks. So you can sort of certain things you can actually automate on the web. Some of the common failures. Where is the model failing? A lot of times model oscillate between two web pages or get stuck in the loop. So like, the agent says, oh, I'm trying to solve this. They go to this page and then they kind of forget what they've done. So this notion of memory, persistent memory is missing. Some of these can be fixed. Sometimes it correctly starts performing tasks and then it undoes them. And sometimes agents stop exploration or maybe execution too early. So it's trying to solve the task and says, I'm give up. I can't solve the task. I don't know what's going on. And then they stop too early. There's also some failures in visual processing. So for example, sometimes clicking on the wrong item. I'm trying to search, I'm trying to click on something, but I click on the wrong thing. Identifying specific items in complex web pages, because sometimes like web pages can be fairly visually
Complex.
overwhelming. There is a lot of complex, and so you have to kind of and also sometimes you see spatial reasoning. Models are getting better. Like if you say, hey, what are the prices of products in the first row, right? If you have multiple rows, so kind of like the model has to understand what the first row means and kind of like have to figure out what the prices are, right? What we need to do, we need to definitely improve reasoning and planning over long horizons. And planning over long horizons is something that people in robotics, have been dealing for a long time. We also want to allow agents to search or maybe execute and coordinate multiple instances in parallel. So you can kind of like want the agents to explore what possible solutions could be or do some form of self-reflection, try to correct the mistakes, ask for clarifications or confirmation. So using the loop kind of setting, human in the loop. We definitely need strong visual language coding models. And also there's a lot of work on identifying appropriate level of abstractions for agents. Do you rely on HTML? Do you rely on screenshots? Do you rely on APIs? Because a lot of times, if you have an API, it's easy to deal with APIs, where I can just request what I need and I can get the answer instead of actually going on the web page. Of course, many real-world tasks will require a lot of visual grounding to effectively solve, complex problems like tasks involved like PowerPoint, Photoshop, and to develop these strong general agents, we'll need to train and build very strong, visual language
Vision.
models.
So,
So, yes,
so, so what's mattering here the most, like the long-term dependencies or the short-term dependencies? So, because for my visual models, I believe the short-term dependencies matter more. What's in the page, uh, they are highly correlated. And for
right.
the text data, what page I'm landing next is my next biggest task. So, what are we really seeking here?
Yes. So let me. Yes. So that's a very good question. I think that this is where planning kind of models become very important. So where you can actually try to plan or try to search what the right thing you need to do. So which is exactly what we're going to talk about next, which is that kind of like research or inference or test time compute for these large language models. Okay. So one of the problems with pretty much all of the agent models is that this notion of exponential error compounding in agents. So, for example, if I'm 90% correct taking an action, after 5 steps, I'm only going to be 60% correct. And after 50 steps, I'm going to be 0.5% correct, right? And so to achieve kind of like a high level of success, you actually need to be very precise in terms of solving every single step, right? And this is where it becomes very, very difficult. Like even if you're 99% correct, if your task requires to take you 30 steps, you're only going to solve 73% of the tasks, right? Which is pretty low. And this is where the challenge comes in with these models, because if you just blindly try to execute, your mistakes will accumulate, right? Your error will compound, and it's a very well-known problem in the community. And of course, if I have, let's say, if I have an agent that's booking my flights, I can't I can't have an agent that's only 73% time correct, right? It's like, most of the time it books the right flight and sometimes it books the wrong flights, right? That's unacceptable. And so this is where robustness of these agents, or this is where some kind of like search is going to be very, very important, or some kind of like human in the loop, where the agent estimates uncertainty, like, oh, I think I'm doing something wrong. Maybe I should go back to the user and ask the user to correct or try to redo the task again. So let me show you what that means. So local decisions have global consequences, right? So for example, let's say I say, add coconut milk to my car. I can click on element ID 31. I can get to the next state. I can click on element ID 24 and then so forth, right? There's a lot of things I can click on. There's lots of actions I can take. And let's say, it's kind of like a tree given here. I click on something else or I search for something else. I get to the next state. And then here I do the same. And then, there's exponentially many trajectories that I can take in that space, right? Because there's exponentially many configurations I can go over. And let's say this is the correct answer. But if my probability of clicking on this is 0.1 and probability of clicking on this is 0.5, if my agent makes the wrong mistake here, it's going to be very hard for me to find this path, right? So it's a general kind of like notion of the search problem that in machine learning, it's a very well studied problem, right? One thing we can do is we can do what we call search by repeated sampling. Very simple idea, a naive idea, is to say, okay, sample actions from your large language model until you solve the problem, until you hit the stop. Let's say this is your sample. And then you say, evaluate the resulting trajectory. You can look at the trajectory and say, have you solved the task or did you not solve the task? If you haven't solved the task, you repeat. You generate another set of actions, right? And so this is what's called rejection sampling. And it's surprising that, if you've looked at all of the reasoning models that we have today, like O1, DeepSeek, models that can solve complex math problems, for example, they're all built on this idea of rejection sampling, right? Given the math prompt, you generate sequence of thoughts or sequence of thinking tokens, and then you see, have you solved the task or not? And then you do this rejection sampling. You sample 10 times, and then you see for which one you solved, for which ones you didn't. And if for certain things you've solved, then you can, use supervised fine-tuning or use some reinforcement learning to improve those. So, this kind of, notion of rejection sampling, it's a very, very simple form in statistics. This is something that you'd cover in the, maybe second undergraduate year in statistics. But once you scale it up and you apply it in these fairly complex environments, it actually works reasonably well, right? And so here you kind of, you sample these paths, hoping that you will hit one of them correctly. Now, of course, your state space is exponential. And, if your model is not good enough, you will never find the right sort of solution. But what we find is that search by repeated sampling helps. What that means is that, the blue curve basically shows what we call pass at 10. So you're doing 10 runs, and out of those 10 runs, you see how many of the tasks you've solved. So the baseline is whatever the baseline is. But here, if you kind of like sample multiple times, at least one time you would solve the task, right? And you see, the more you sample, the more search you do, the better the results are. But of course, the space is exponentially large. How can we guide exploration, right? And the key idea here is to apply the value function to intermediate nodes. So let's look at the algorithm, a simple tree-search algorithm. So it's a best first search algorithm. So what's the ingredients? You have a baseline agent that proposes actions. Okay, so let's say have an agent, looks at the web page, and it proposes 2 actions. You have to have a way to backtrack in the environment. So in other words, like if you go a particular state, you have to wait to say, well, actually, I'm in the wrong state, go back to the previous state. And then you have to have a value function. And you can think of the value function that basically gives, the definition of the value function is the expected probability of success. So you can think of the value function that gives you the score that's telling you what's the probability that you will solve the task if you're in this state, right? Or if you're in a particular state, right, you take the current state, that's the image, you take all the previous observations, And then you say, okay, given this, what's the probability that I will succeed in this task? And you have to build the value function yourself. It could be another language model. Sometimes we use LLM as a judge. So for example, here, if I'm in this state and I take these two actions, I look at this state, I look at this state, and I say, oh, the probability of me solving the task is better here than here, so maybe I should proceed with this and ignore this state. So in this work, we actually prompt a multimodal LLM to act as an evaluator, right? So we're basically using LLM as a judge, which basically says, given the state and a sequence of states, give me the probability that I can successfully complete the task. Now,
Basically,
LLMs as a judge. Yeah, sorry, go ahead.
basically the same thing that autoregressive models have been doing. So
Yeah, exactly. Exactly. Ultimately, you'd want to build your own value function, just like you want to build your own reward function. Sometimes these value functions, there's another term for it. Sometimes people call it process reward models, right? But it really is a score that's telling you how likely you are to succeed in your task. And if you have a very good value function, then search becomes more efficient. So here's an example, right? Let's say I give you some task. Can you add this and the other canned fruit of the same brand that looks like this, but red instead of brown to the comparison page, right? So let's say, with a search, I can sort of say, okay, I take an action, and let's say after this, the model gives me 4 possible actions. The 4 likely actions. The probability of those actions is 0.45, 0.45, 0.45. So which one do I take, right? So GPT-4o, you just randomly sample one, you go here, right? And then you evaluate and say, oh, it's like my value actually goes down. So like, this is not a good state to be in. I go to the next one. So I backtrack to the previous state and go to the next state. And now my probability is improving. I say, okay, I'm doing something good. And now I'm doing something really good. And then I end up on the web page and I'm realizing that's the wrong state to be in, right? Like I've just did all this work and there is no way I can solve the task at this point, right? Because I'm close to finishing, but I can't. I backtrack, I go back to here and try to do it again, right? And again, there's 2 choices. I take this one. This is looking good. And again, it doesn't solve the task. I retract, I go back, and then I solve the task. So you can see this is more of a search, and you can implement it in different ways, but it's a search that sort of takes more time, but it's a way for you to try to explore the environment and kind of do the search in a more guided way, right? So some results that we're seeing on Web Arena, we're seeing improvements. On Visual Web Arena, we're seeing improvements, right? So what that means is that searching through certain things actually helps us quite a bit. It's sort of like these good examples we see sometimes on Visual Web Arena. I ask you to buy a blue polo shirt. And then the model tries to navigate. It ends up on a web page only with black polo shirts. And the model says, okay, there's no blue polo shirts. So I'm done. I can't solve the task. But actually what happened is that a couple of steps before it chose the wrong color or it sorted in the wrong way. So it took the wrong action. So if you can retract back and take the right action and correct your action, you would find the right solution, right? So these kind of ways of doing search, and this is called the tree search. There are multiple ways of doing it. You can run parallel agents. They can communicate with each other, so that because you basically want to explore the space and try to see how you can solve the task more efficiently, right? So obviously, having a good value function is a key. So, this is on a subset of Visual Web Arena task. We kind of like see, as you're searching for more and more, performance goes up. And again, having a good value function, like sometimes people train this value function, sometimes using LLM as a judge. That's important. And of course, there's a lot of headroom for improving both. You want to have your agent policy to be good. You want your agent to be smart and understand. And also you want your value function to be good so you can kind of guide this exploration of this exponential environment efficiently. Here's one example, right? I need something like this for my apartment. Can you add one to my wish list? Right? So the model would kind of like go and sort of search through different things and eventually, successfully find this particular item and add it to your wish list. Right. I mean, it's just one example, but it would be nice if you kind of like take a picture of something, say, hey, like find me something like this, put it on my wish list. Now, some of the limitations. With the way that we're implementing search, it's fairly slow. This is more in the engineering setting, right? Because a lot of times you take an action, you want to be able to come back to the action. So what sometimes, you store action in the queue and then you replay them again. So it's more of an engineering question of how do you do backtrack. But there is also more of a technical question dealing with what we call destructive actions. So certain actions you take on the web are difficult to undo. So for example, if you ordered an item, you can't basically change your mind and say, no, unorder it, right?
Yeah.
Or if you booked a flight, you can't say, no, go to this state, flight, right? So certain actions you can recover from. So you have to be careful how you deal with those actions, right? A lot of times this is where humans would be involved. But generally, any state that changes the state of the environment, you have to kind of deal with, right? Ordering something, booking, and again, it's difficult to do it because it's difficult to explore, right? You can't say, again, as I mentioned, you can't book the flight, book the hotel and say, no, go back. Let's book another hotel, right? You can't do that. Like you basically, right? It's certain things you can do on the web. Now, what are we doing right now? Obviously, search as a policy improvement function. So you can think of search as providing you what are the good sequences of actions you take to solve the task. So if the search finds one sequence and solve the task, that becomes your training data. Obviously, improving the value function by fine-tuning instead of prompting, building good value function that can guide your search is very important. And of course, interesting question is to explore computational trade-off between improving your base model versus doing more at test time. What we call test time inference compute, right? And this is kind of the two things that people are working right now is, do you improve how like you want to have your base model to be good, right? How do you build the next GPT-5, GPT-6, right? The next Llama models, the next Gemini models, so that they're generally good, versus how good your search techniques should be so that you can solve the problem. And the other question, if we don't have a perfect simulator, how can we collect data at scale? And that's a very interesting problem as to how do we actually, because the problem with a lot of agentic capabilities today is that there doesn't exist a lot of data where you give it a task and you have very precise data on how to solve the task, right? A lot of people solve all tasks all the time, but it's not the kind of data that's available to you online. So when we're training these big large language models, we typically crawl the web, images, and we kind of create self-supervised learning problem. But how many times you can find information online where somebody tells you, hey, if I'm searching for, if I'm trying to buy this item, these are the steps that I need to do to buy it. So a lot of times that data doesn't exist because that's the data that humans do, but nobody's recording, right? And there's a lot of privacy concerns there because I don't want anybody to kind of like see how I'm solving tasks online. And so this leads us to the problem of how can we build internet scale agents. And one of the things that we see today, a lot of existing agents right now often trained offline, right? And then they deployed as zero shot as agents. Ultimately, I do believe that a lot of these models are going to be trained online. You'll have agents crawling the web or controlling your computer and learn by interacting with the environment. But because of constraints right now, a lot of this work is now being done offline, which means that you collect the data, you store the data, you train your model. And then maybe you go collect the data again, store it, and then train again. Right? And so one question we were asking, at least as an exploration question, can synthetic tasks, synthetic data help us to scale training of these agents? Okay. And, we've sort of looked at something that we called Insta pipeline, internet scale training for agents. And one of the key ideas is we're using Llama models, which is open source models, to generate and verify synthetic agentic tasks. So the idea here is that you're asking your model to generate a task, you're asking your model to solve the task, you're asking your model to verify your task, and then based on that, you can basically create training data, right? And then you use this training data to train your model and it becomes better. So it's almost like a self-improvement by model sort of, generating its own tasks, solving them, and improving. That's sort of the high-level idea. So let's see how we can do it. Let's look at the task generation. Okay. So we found that, for example, given some domain like Mercy Ferries, it's like some kind of website in the United Kingdom, in the UK, right? Let's say you propose an average task. So for example, with Llama 3.170B instruct model, we ask the model to say, describe me what this website is. And it actually does a pretty good job, right? It says Mercy Ferries. It's the official website for like some famous ferry rides, in the England and whatnot. You can plan a journey. You can plan your journey by checking the ferry timetables. You can book the tickets. You online for for cruise services and so forth, right? So it's like some website, and we're prompting the model to say, hey, generate me some tasks that humans can solve. We give it some prompt, we give it some examples. It's a few shot type of setting. And then what we found is that across a lot of different websites, I think we've looked at something like 1 million different websites, a lot of tasks that we're generating, there's a heavy tail distributions, and a lot of tasks involve information retrieval. So just because it's the easy to construct, like find me this information, find me the opening hours of this thing, right? And more importantly, when we were designing these tasks that do not modify the state of the internet, right? So, for example, we can book, we can add, anything that changes the state of the real web, we don't do, right? And that was done primarily for safety kind of reasons, so that we don't accidentally kind of get banned by websites, right?
But
So, yeah.
but do you think actually these tasks do not modify the student? Because if even I'm looking for, say, black polo shirts, the Amazon is noting that data and it might just surge up the prices. So at some point they do.
Yes, I mean, yeah, I mean, some point they do, but it's less about like us ordering or placing orders or something. Yes, they might be the case that we keep searching for certain things. The certain websites may say, "Oh, there's an interest. Somebody's keeps looking for those things," right? But the way that we've done it is we basically never visit the same site more than a few times. So we never go to Amazon more than a few times. We never go to eBay more than a few times. We basically try to go over like 1 million websites. So we try to go into breadth rather than depth of a specific domains.
Uh, yeah.
And so some of the tasks, like so here's some example tasks that the model generates on specific web pages, right? Some of these tasks are diverse. So for example, on fontsadobe.com, the model actually says, hey, browse me all the fonts suitable for a children's book, right? And so this is a task, right? And the question is like, if I give this task to the agent, can it actually go and solve the task? Or find me the top rated free productivity app for iPhone, right? Or find me a free and popular theme for a personal blog. Or read Google term of service for using YouTube. Some of these tasks can identify facts. Like, again, these are tasks that are generated, the model generates by looking at the website. So for example, it says, like if we go to ancientsymbols.com, you can say, look up the meaning of the Om symbol in ancient cultures, right? There's like bunch of Blue Ridge County. Find a scenic hiking trail in the Blue Ridge Mountain. It's some website, some local park, right? That talks about Blue Ridge Mountains. You can also, some of the model has some broad knowledge. So for example, there is this website, Scottish website, and I can ask it view the latest fabric designs by Thomas Bastier Studio. Right, it's some obscure Scottish design studio that it's a very local. Nobody knows about it probably, but the model is actually able to generate reasonable tasks, and it's a lot of these tasks are also grounded. Right, to solve this task, you have to go on this website. If you're browsing the latest fabric design, you have to be on this webpage. That's the latest fabric design by this studio. Right. Okay, so that's the task generation. Right? So now let's look at how do we know when the tasks are solved. So what we do is we actually, given these tasks, then we execute these tasks on the real web. We ask the agent, kind of like what we've seen in Visual Web Arena, go solve this task, and then try to evaluate. And the way we evaluate it, how do we know whether the agent actually solved the task? Is we observe a sequence of actions and the last observation. So we have chains of thoughts, sequence of actions, the last observation, and we estimate the probability of the tasks as a success in the final step. So we're trying to estimate what's the probability of the success given a sequence of actions and the final state. And it's called the task description. So this representation, it's exactly like what the value function is, but just at the last step. Right, so it's exactly the same what we've done using LLM as a judge, and here we're using Llama to rate the confidence of the task itself on a scale from 0 to 1. Right, so we're prompting the model to say, hey, given this task, given these actions that I'm taking, given where I end up, what's the probability that I'm solving the task? It turns out that for agentic sort of models, evaluating is a much easier task than actually solving the task, right? Which makes sense. It's more of a, if I give you the trajectory, it's easier for me to say, is this correct or is this not correct?
Okay.
Yeah, but it's
Is it?
much
It's
to generate
more
it.
like the Q learning that we do in reinforcement learning, right?
Yeah, something similar to that. That's right.
That.
Um, and so we can kind of estimate the success, right, using LLM as a judge. And out of, let's say, 150,000 tasks, about 15% are rated as success with high confidence by these llama verifiers, right? So we can generate a lot of tasks, and about 15% of the tasks, when we actually attempt them on the real web, the model would say we solved them, right? So for example, here's an example. Let me show you an example of a real kind of task, because we've been working with some other researchers on kind of like finding invasive plants in North America. Let's say there's a website, Invasive Plants Atlas. Given this website, Llama model generates a task. It says, find me invasive plant species native to North America. So that's the completely synthetically generated task. It's not human generated, it's model generated. The agent responds, and I say, solve this task. The agent basically says, to find the invasive plant species native to America, I'll first click on link all species. And it kind of like, and that's what the action space looks like. It basically says action key click. There's no arguments. Target element ID 12. So we're clicking on target element ID 12. That's the 12th element using set of marks representation, right? And then it goes to the next stage instead of like, okay, to find invasive plants, again, I first click on the home and so forth. And then what it does is actually tries to click on sources, but it accidentally clicks on home. So it needs to kind of sources. So it sort of like missed, it sort of did the wrong action. It clicks on home instead of sources. And then eventually it clicks on sources. And then it's sort of, to find invasive plants, I will first click on the link fauna under the native Finch taxonomic references, which actually does the right thing. It clicks on the right thing. It lands on the web page, and then it sorts, link based on US, how native it is to the US. And then it sort of finds the right information, right? And
So
so the first 165 plant species on this webpage are the list of invasive plant species in North America.
yeah.
Was a
So
question?
yeah, we have a doubt from Mr. Ansh. He's asking, okay, what if the generated tasks are hallucinations that are impossible for a particular site? And how do we maintain
Yes.
that AI model cannibalism isn't due to the synthetic data? Like it is telling it to say, do something, and then it's impossible. So my model isn't able to do it. And then it's evaluating on its basis that this task was given to this model, and then we are unable to do that.
Yes, it's a very good question. So the way that we kind of like doing it, right, is let's say the task is hallucinated task that's impossible to solve, right? We're still going to attempt to solve it, right? The model will try to attempt to solve it. It will try to go through the website and try to do its best to solve it. And then given the sequence of trajectories, there's two things. Once it hits the stop action, it means that the model says, I solved it. I can no longer proceed. And then what we do is we give sequence of actions and the state back to the model and ask the model, have you solved this task?
Okay.
Right? So if it's a hallucinated task and you couldn't solve it, with very high probability, the model itself will say, like, no, I didn't solve the task because I don't end on a state that actually shows me the right solution. Now, it could potentially hallucinate. I'll show you some numbers where the model actually didn't solve the task, but the model can say it solved the task. And the success rate there is about 90%. So out of 100 proposed tasks, 90% of the time it will say it solved the task. And about 10% of the time it would say, yeah, I solved the task, but it actually didn't. Right. So
Yeah.
there is some errors that are happening, but these errors are kind of like fairly small at this point. Right. So if it's a completely hallucinated task and the model just tries to solve it and can't, most likely the model will say, I'm not very confident that you've solved the task because we prompt the model to kind of like rate the confidence as well. And we, instead of doing it once, we're actually running multiple, an ensemble of models to see like, have you solved the task? And as I mentioned before, evaluating whether you solve the task or not is much easier than actually solving the task, right?
Yes.
Because, for example, this example of blue shirt kind of like thing is that, well, if you have a polo, if I'm asking to buy you polo shirt, blue polo shirt, and the agent ends up on a web page with blue polo shirts, and you basically say, okay, here's the sequence of actions that I've taken, here's the state I'm in, and this is what I'm trying to solve. How confident are you that you're solving it? And again, the success rate there is about 90%, right?
Okay.
So it's decent in terms of verifying your actions. And so
Yes.
here, there's a particular
Aavesh.
stance despite some makes the wrong thing. The llama verify validates its trajectory is successful with confidence one. It basically says, I think you find the right information.
Okay.
It makes mistakes here. Like sometimes the model say, yes, I'm confident you solved the task, but actually you didn't solve the task, and the accuracy of that is about 90%, right? So here's an example of the agent, browsing the web, coming up with tasks. Find the opening hours of Sagrada Familia. It's a famous church in Barcelona. It actually goes, it finds Barcelona, it searches the web, looks at like the information, and then finds the answer. It has a stop, and this is the kind of what the answer is. We'll find information on the European Union's climate action policies, right? It kind of like goes to the European Union, it clicks, and it sort of eventually finds, these are the reports about, climate action progress, right? And so again, these are the tasks that the model comes up with, or like this one, right? These are the tasks that the model comes up on its own, executes these tasks, finds the solution, and verifies itself, right? So it comes up with its own task, executes, verifies. There is no human involved in this. Now, how do we go to the scaling it up, right? So for the scaling up, what we've done is we basically use common crawl page rank to find the important websites. We start with 1 million websites. The model is actually pretty decent, about 97% accuracy in terms of detecting and filtering harmful content. So for example, if there's like violence and some harmful content on the website, we kind of we eliminate this. We're not perfect, but through filtering, there's like personal identification kind of like piece, a lot of things that we filter out, and it reduces the number of web pages that we're looking at. It's about 90% in generating feasible tasks. So what that means is that, if I generate the task, 90% of the time I can actually, kind of generate something that is going to work. Or, so we think of these tasks as kind of like, and then about 10-11% of the times it like generates like hallucinated tasks or tasks that completely unfeasible to solve. And with about 80% accuracy in judging successful task completion. So what that means is that if I actually solve the task, the model is about 80% successful in terms of saying, yes, you actually solved the task. So there are mistakes, absolutely. We're going to end up with tasks that are slightly hallucinated. We're going to end up with trajectories that are not correct, but the model will say, yes, it's correct, right? Because there's no perfect solution, but you see like with these models, the numbers are pretty high. This was done with Llama 3.1. With Llama 3.3 right now, I think these numbers are increasing. Right. And so it's a first kind of, initial proof of concept that we can actually at scale have these agents generating tasks, solving them, trying to evaluate like, have you successfully solved them or not, right? And repeat this process. So I can see in the future a setting what we call an online learning, where the model comes up with a task, execute the tasks, tries to evaluate, have you solved the task? And if it solved the task, it can use it as a training data to improve itself. So it's kind of like going through self-improvement. And then what we see is that for some of the tasks like web links, mind to web, these are sort of like step accuracy, where given some history, I'm trying to, identify, am I clicking on the right action? Am I taking the right, am I clicking on the right item? Do I take the right action? Do I search for the right thing? These are sort of what we call static kind of environments. Our initial results show that, we can actually improve the step accuracy. What's more interesting, we can improve generalization. So training with only human demonstrations, like a human solving the task, you can struggle with generalization, meaning that, when you go to some website in the tail of the distribution, those models don't tend to work very well because when we collect the data with humans, we can only collect not that many domains, right? So it's always like collecting human data is actually very very expensive and laborious. um, but adding synthetic data plus human data improve generalization by it has substantial improvement in kind of like making the model generalize better to completely new domains, right? um, Now, there are about 385 million unique domains in the common crawl page rank, suggesting you can kind of like scale it even further up. Um, and then there is sort of work moving towards online RL. So online reinforcement learning, you can think of it this process that I've described, but done online. Online basically means that on the fly, I generate the task, I try to solve the tasks, I verify whether I solve the task, and based on this, I update my model parameters. And now my model gets a little bit better. And I repeat this process. So you can think of these adaptive agents that constantly kind of like exploring the environment, learning from the environment, updating the parameters. I think that that's something that we will see more and more in terms of agentic capabilities, where these agents will, again, as I've mentioned, maybe it's on the computer, on the web, they will explore, and by, generating their own tasks, trying to solve the tasks, and then, verifying whether they solve the task, gives them the training data they need to kind of like keep improving. Right? Um, Now, in terms of just to summarize what we've talked about Visual Web Arena, right? We've talked about a way of designing this simulator to rigorously evaluate and the capabilities of these autonomous multimodal agents. We've talked about inference time search, designed to enhance the capability of these models on realistic web tasks. So you can have like strong value function, you can actually be very good at doing this guided search to solve these complex tasks. And we've talked about data pipeline for large scale generation, verification of synthetic web tasks, right? Powered by these by Llama models. And obviously, one thing that I haven't talked about is on safety and robustness, especially in the age of autonomous systems. How do you make sure that these models are robust? How do you make sure that these models are safe, that they don't take any kind of bad actions or make something that's sort of you're not supposed to do? And so, for example, one example, again, this was done at CMU, is you can build these adversarial attacks on multimodal agents. So, for example, you can modify the content of your web page. A lot of these systems, they kind of look at the images, they caption the images, they look at the whole web page. So you can sort of modify the web page so that you can, the captioning system can give the instruction to tell the model to leave a 5-star rating for your product.
Yeah.
And let's say the model is looking for polo shirts, and it ends up on the web page with with other t-shirts. And by hacking, if I'm able to influence these agents, then the agent's going to say, oh, these are fantastic t-shirts, 5-star rating, and then it goes continue searching for polo shirts, right? We don't want that type of behavior, right? So I don't want a behavior where like I can hijack somebody's agent so that it kind of leaves me, for example, good feedback, right? This is just one example, but there is a lot of work on sort of trying to figure out what these safety and robustness and adversarial attacks would look like in the age of autonomous agents, right? Especially when these agents actually take actions on your behalf. And this is one example. Claude, Anthropic's kind of like models, they had an agent, a computer use agent. And so, for example, they said, even we were recording demonstrations, we got some errors, and Claude accidentally clicked stop in a long-running screen recording, causing all footage to be lost. In another, Claude suddenly took a break from our coding demo and began to produce photos of Yellowstone National Park. Right. So it like the Claude like does some kind of like coding, and then it takes the wrong action and does something completely different. Right. And this is sort of points out to the settings where these models are not robust enough. And when you're executing sequence of actions, if you take the wrong action, the model kind of can veer off into some weird space and do something else, right? So that's where we are. Thank you for listening, and I want to thank all of my students at CMU who basically doing a lot of work in the space of robotics, large language models, and sort of these agentic capabilities.
Yeah. So Let me please ask if the audience has any doubts, so we can move forward with more general doubts.
Sure.
Yeah. Uh, Please. Okay, so we have another doubt saying any alternatives to VLMs coming up in parallel. So, is there any other technology that we are working on?
Sorry, what was except for like kind of like models running in parallel? You mean?
Uh, yeah, like uh, in VLMs, I believe it would be more like the multi-head attention thing, where we expect bunch of VLMs to be running in parallel to acquire specializations.
Yeah, so I think that this is more. It's a less we less. Like I think that when we look at VLM, yeah, you can have like multi-headed attentions. You can kind of like improve these models. But when I think about tree type search, like what we've done here on the inference time compute on the inference time search, you can think of these agents running in parallel. It's just a matter of how you structure it. There's a lot of work on kind of improving. Right now we've been doing it more of a sequentially. We kind of like take steps in a greedy way, and then we backtrack and try to kind of like greedily find the best path. But you can imagine agents that can run in parallel and communicate with each other and sort of do guided search that way. A lot of it comes down to compute, how much compute you need to spend, how much compute you're willing to spend to actually get to the right answer. So
Okay, I believe that answers it. So, next question is what other promising developments are happening in this field, reasoning models apart from the VLMs?
I think that what's interesting happening in the space right now is obviously VLMs, but it's interesting to see how you can start combining visual language model with reasoning models. We're now getting to this point where we have very good reasoning models in math and STEM and where it's like very precise, what we call verifiable domains, where I give you the math problem, there's only one answer, to the point where you have these agentic capabilities that can solve more general, more broader tasks. One example that we're seeing today is something that's called deep research. Models that can kind of like find information, compile the report for you, do several steps of reasoning. Maybe in order to get the right information, they would execute the code. Maybe they would go to specific websites, find the right information, and sort of compile everything on your behalf, right? So this is kind of like the next evolution of these kind of more like knowledge workers for you, right? Um, and again, it's a combination of visual language models using APIs, combining reasoning models into these more complex systems. And of course, the other parallel is kind of these computer use agents, right? Agents that can take over do a lot of tasks for you, general tasks for you on the computer, right? Populate your Excel spreadsheet, populate your Google spreadsheet with information you can find on the web. Um, any sort of routine tasks that everyday tasks you're doing on the computer, those tasks can be automated and can be replaced by agents.
Okay, and I hope that's answered. The next question that we have is when evaluating a model, we rely on a LLM, but following a famous tweet that LLM was confused between finding the bigger value between zero point 0.1 and zero point 0.9. So that simple task was failed by the LLM. So how do we rely such big task of comparing some outputs and evaluating them on a LLM when it fails on simple math sometimes?
Yeah, so sometimes it fails on simple math, but sort of like solves more complex math. It basically points to the point where like our reasoning models have to be improved, right? And so I think that obviously even for these web tasks, for some of the tasks that we're generating, there we generate correct task, but it doesn't solve it correctly, and the model still says yes, it's correct, and that becomes the noise because we're still training on this. So you have about 10% of the noise that goes into the training procedure, right? And the hope is that through the process of learning, the model still trains on 90% of the kind of like clean or kind of like good tasks. And through the process, iterative process, this noise will shrink, and become smaller and smaller. That's just an empirical question that we have to kind of answer. Perhaps there are also better ways of doing things. Like, for example, you can imagine where you're not just saying, have you estimated, task or not? You can try to do search when you're executing the task, or you try to estimate uncertainty. And you can also use ensemble methods. There's a lot of ways you can do to try to reduce this error, but ultimately, it's very hard to do, right? Ultimately, we'll have to have some form of human in the loop that verifies some of these tasks, and we build these human verifiers to try to avoid some of these mistakes that the model is making. Right now, what we've built at this point is fully synthetic. There's no human involved at all. But I think if we can get even like 0.01% of the humans who would like look at some of these stuff and verify them, that would help us. So I think that the future is going to be humans are going to be involved in one way, hopefully, in sort of just to filter out these incorrect trajectories.
Uh, One last question before we follow to the more general questions about you regarding this topic. Uh, Vineet is asking, what are the alternatives to best first search algorithms in the repeated sampling? Like we are using a greedy approach here, but although like for my first instance, it might get a lower value, then
Yeah,
in the next step, we can get a higher.
that's a very good question. Are there other techniques? I'm sure there are. We haven't explored. We've tried to explore a few things, like we kind of like A-star search, greedy kind of like decoding strategies. We just found whatever we did, we found worked the best. But there is absolutely no reason why the greedy search, kind of like greedy decoding search, or like the A-star type search, is the best search. I think that there needs to be a little bit more exploration. But I do think the type of search itself is less important than compared to having a good value function. Because the value function, imagine you had an oracle value function. Imagine a human would look at like and tell you like, oh, like out of these three things, no, you should click on this thing. Because humans are also very good at like navigating the web, right? Because we also have some form of a world model where like if I'm searching for toothpaste, I know I have to go to like bath section. Right, I have sort of like this high level knowledge of what I need to do, and humans are also very good at correcting mistakes. It's one of the things that we're also trying to do is to correct mistakes, and that's what the search is trying to do, in a sense that if I'm trying to accomplish the task and I'm almost getting to the end and I'm seeing like I actually haven't done what I need to do, maybe condition on this thing, I can actually go back and refine what I'm trying to do. So there's notion of kind of like search by enhancing and repetition. And again, the value function here is the most important piece, because that's essentially telling you how good your search is, rather than the search itself, like the search technique.
Okay, so that marks us the end of these doubts. So we'll be moving forward to the more general doubts that our students have gathered. I hope this session is well received by all the students on LLMs and autonomous AI agents. So, moving towards your life experiences and the contribution that you have made towards science. So, the first doubt, it's my very own doubt. So,
Sure.
well, you have given the dropout network. So it's very naive idea. Like, so my model is overfitting. So let's do one thing: take some neurons and tell them to just stop contributing when I'm evaluating randomly. So
Right.
what was the thinking process behind this idea? Because this naive idea, it seems to be very naive, because honestly, the three laws of motion, they seems to be really naive, but back then they are still really
Yeah.
important.
Yeah. So the idea of dropout really came from the notion and it was kind of like also pioneered by Jeff Hinton, my advisor at the time. It was really designed or came from Boltzmann machines. So there is a class of models called restricted Boltzmann machines and Boltzmann machines, and these are stochastic systems. And then the way you do inference in these models, the way you kind of learn what these models are, is that given the data, you compute the probability of hidden states, and then you sample from those probabilities.
Okay.
And so the model is inherently stochastic, right? And these models early on were learning to generate digits. Like if you've heard about deep belief networks, when I was a PhD student, like we worked a lot on these models. And that gave rise to the notion of the dropout, because the notion of the dropout came from, okay, you have these stochastic systems where you're sampling hidden units with certain probabilities. And then the dropout was kind of, a little bit derived from that perspective, which is like, okay, if we try to make our feed-forward neural networks be a little stochastic, what would you do? Right? And we had a brilliant student, Nitish Srivastava, the first author of
Yeah.
this paper. He was a master's student at the University of Toronto. He actually came from IIT, one
Bombay.
of the IITs,
Yeah.
IIT Bombay, right? And he was a master's student. He just tried this idea, right? He basically said, okay, if we have the system, we sample, and it basically showed good empirical results. And that's when the idea of a dropout came to life. And then there was a lot of follow-up work to trying to understand like what type of regularization these dropouts are doing. But yeah,
Yeah,
a
that's
lot
what
of these ideas
scaffolding.
again came from these from our statistic Boltzmann machine models, because we are sampling in those models. We are sampling hidden units. We are sampling hidden, variables. So they're always like 0, 1, for example, right? And that's the idea that came, like maybe we should stochastically sample some of the, hidden units in feed-forward networks.
That's amazing. And moving to the next question that we have. Okay, so what's your take on DLLMs or diffusion large language models like Mercury Code by Inception Labs? So that came out recently in March.
Yeah, yeah. So diffusion language models is an interesting idea. I haven't looked at them very carefully. I know some people have looked at them. I have one of my students is working on diffusion models. It's still early to say. One interesting thing about diffusion language models is the speed they can sort of generate, kind of like faster,
Yeah.
and they can sort of start with certain concept and then diffuse it all the way to the sentence, as opposed to doing autoregressively. So it's definitely worth exploring right now. It's still too early to say whether they're going to be useful or not. There is something about autoregressive models, especially now with these sort of reasoning models, where I can generate a sequence of tokens, I can condition on them and say, hold on, let's re-examine again. And it sort of generates another path. So it's almost like a tree search where you kind of like explore one path and you say, no, that didn't give me. And condition on this, I start exploring another path. Condition on this, I start exploring another path. So this notion of conditional sort of generation with autoregressive models and self-correction seems to be very powerful. We'll still have to see. I think it's a very nice research topic to see, diffusion language models. So we'll see whether they will work, or maybe they. I mean, whether there is an alternative to the autoregressive models that we have today.
Okay. And the next question for that is, what are the security concerns in the advancement of AI? Do you see AI entering the field of cybersecurity? And if so, will it become a threat to the security of individuals and company, or will it help?
I think
Yeah.
right. So I think that just like any technology, it can be used for bad and good. I do see a lot of work, especially on the agentic side, on the cybersecurity domain. So there's like, people are building simulators on, let's say I have a computer, right? I have, it's simulate. I mean, it's not the real computer, but let's say I have a computer, and I'm asking my model hack into this computer,
Yeah.
right? And I give it a task, capture the red flag, like get in the computer, find the information, retrieve that information from me, right? And so there's a lot of line now in cybersecurity. People are studying, okay, given all the information I have on the web, all the code I can train, all the cybersecurity vulnerabilities I have, can the model synthesize, certain attacks that I can do against, a computer, and then try to capture the flag, and then um, you know, uh, 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 and so I think that there is definitely a lot of work. It's too early at this point, but it's definitely going to be the case that these models will be able to exploit some vulnerabilities. But just like as you explain vulnerabilities, you're going to have agents that will kind of figure out, like you can basically say, okay, here's an agent, explore vulnerabilities on my system, and the agent will explore and you can fix those. vulnerabilities. So it's kind of like, as soon as you have an attacker, you can kind of use it to fix your system. So I do think that in the space of large language models, cybersecurity is definitely going to be one of, again, think of the large language models as consuming everything there is on cybersecurity, all the books that are written, all the code that is written, all the previous vulnerabilities that are known, right? Once the model consumes all of that, it can synthesize, it can, it's like Lego blocks, put different pieces together and say, okay, let me explore security vulnerabilities in this system and just try a lot of different things. And so I think that there's going to be kind of both sides. You're going to have agents that's trying to explore vulnerabilities. But at the same time, if you have those agents, you can start fixing those vulnerabilities. So it's kind of, I think, it's a good area of research, and you'll see in both cases, people trying to exploit vulnerabilities and people trying to improve the vulnerabilities of the system, right?
Okay.
Um,
Next question. You have experienced both academia and industry, having worked at Apple as director of AI research and Meta. What are the most surprising differences between the two worlds, and how did working in industry shape your research perspective?
yeah, that's a very good question. What's the difference between academia and industry? So I kind of one of the advantages, I guess, that I have is I get to see both, like how things are done in academia, how things are done in industry. I think that industry goes through these cycles, right? Where right now, industry to some extent is partially leading in AI, primarily because of compute, the access to GPUs, and building large models. But at the same time, open is also catching up. And so I personally like being in academia because there is more freedom to explore new things in academia, right? So that's generally my view, is that, and in academia you don't have a boss. You can, you can have your own research idea. You have brilliant students. You can innovate. You can really take time to think deeply about something and kind of explore that. Industry, on the other hand, depending on when, like I remember in 2015, 2016, when the deep learning was coming online, there was a lot of excitement in industry because people started building and scaling these models. So that's the time to be in industry. In 2019, 2020, nothing was happening. It was a little bit boring, like things were happening in academia. Since ChatGPT, there's more investment. So it really goes in cycles. I like being in both, and I think that again, the nice thing about industry is get to see how these large models are being built, and what's kind of like what is possible if you took it to the kind of like very very large scale, right? But a lot of a lot of new ideas really come, I believe, in academia with brilliant students, because a lot of them get to explore some, like for example, language diffusion models. I think those came out of academia. Dropouts, they
Yeah.
came out of academia. Attention mechanism of the transform architecture was actually developed in 2014 in Montreal. Like the first attention mechanism was developed by some grad student in Montreal. So it's kind of, like whether it's at CMU, MIT, Stanford, or other places, some of the core ideas are being developed in academia, but industry is very good at taking these ideas and taking them to large scale and putting them into the products. Right. So that's kind of, it really depends what you want to do.
Okay.
But I think that today, being in industry is also very exciting, like at least right now, because it is, you basically see what the next 2 years in AI is going to be, and a lot of it is going to be probably be driven by industry for now.
Okay, I was checking, going through the what CVPR papers, this year's CVPR papers, and they were mostly around the LLMs and large language models, and along with some were around the image segmentation part. So a few of them were really close to that. So what do you think the next year is going to be like? Yes, we are heading towards in a total research space. Yes, the entire research
You
focus
mean
on.
like
Yeah.
Yeah, so I think that, I mean, it's good and bad to some extent. It's good that people are exploring these models. It's bad that we might be hitting some kind of local optimum, right? Because if everybody works on large language models, there is still a room of like innovation that needs to be done outside of just language models. But at the same time, I think there is a lot of work that needs to be done in an LLM space. I do think that the year 2025, 2026, you'll see more sort of agentic research and agentic models. We'll just transition from question answering type of systems to like, hey, do this thing for me, do my homework for me, right? And not only do my homework for me, send it to my teacher, right? Upload my homework and send it to my teacher and send an email, with my homework, right? You can imagine systems. I mean, it's probably a bad example. You don't want to somebody else do your homework, but we are going to be kind of like moving into the space where we're going to have AI tutors in education that will work with you to solve math problems. You'll have in medical fields, you'll have sort of assistants that can kind of like give you a little bit of a guidance as to what's going on. You'll have that. There's a lot of work that I think is going to be happening in 2025, 2026. A lot of it is going to be on the agentic side. A lot of it is going to be on the safety side, I suspect, robustness of these models. And I do believe some of it is also going to be in robotics, like actual physical robots. Um,
Yes. Uh,
and of course, there are sort of these big questions of like reasoning. How can we get these models to reason? How can we get them to have some kind of like world model so that they can simulate forward and understand what the future is going to look like. So there's a lot of work that needs to be done in that space, and this is where the research is going to be focusing on.
yes, adding it to for more like I saw this Nvidia's this they released their robots with in
Yeah,
collaboration with Disney. That was really inspiring.
yeah. Robotics is gonna, exactly. Robotics is going to take over because we have digital agents that can be on the web. They can be your assistants that can help you with everyday tasks. But ultimately, we'll move to the way of physical robots, like that will kind of do physical tasks as well.
Okay, with this we move to our last two questions. Uh, Neurosymbolic AI is gaining traction as an alternative to deep learning's brute force scaling. Do you think hybrid approaches are necessary for the next generation of AI?
That's a very good question. In fact, like some of the work that we're doing at CMU is sort of like neurosymbolic AI, right? Like, so this notion has always been that deep learning is very good at feature extraction, but maybe some form of reasoning and sort of high level concepts can be done with maybe combination of symbolic systems and such. We still yet to see what that's going to look like. I suspect a lot of, like, for example, tree search in a nutshell, that's like a symbolic type of approach, right? Because we're not telling the model, hey, search on your own, learn how to search. We're actually explicitly telling it, like, hey, like go through these steps, look at the value function, backtrack, go. So it is an instance of this hybrid system, right? As opposed to just a black box model that does everything internally. So ultimately, there's probably going to be some form of hybrid systems that combine some of these brute, like black box approaches with something that's a little bit more structured, right? It's the question is, with the neurosymbolic approaches, the question is, can we scale them up and how efficient can we learn them? And sometimes like neurosymbolic is also useful for extracting concepts. Like, for example, if you think about these reasoning models, or like if you think about these web agent models that can try to solve on the web, it'd be great if the model, by doing a lot of tasks on the web, would come up with some high level actions. It would learn on its own and say, hey, if I'm trying to do this, like, these are a set of actions that I need to do. Or if it's a math problem I'm trying to solve, maybe I can come up with some high level hypotheses or like hints as to how I should be solving the problem. Like, hey, I should be using Pythagorean theorem, or I should be using kind of like, Newton's law of motion to solve this task, as opposed to like just generating one token at a time. So you can imagine these hybrid systems where we give it some prior information of what that structure should look like, and then they go and solve it. Or they through this bottom up, they kind of like solve the problem, but they extract this high level structure, so that it's easy. For example, if I'm a tutor, right, and I'm tutoring somebody, it's useless for me to generate 10,000 words explaining like what is 1+1, right? I need to have some form of like, high level representation so that I can communicate with you. And if I'm trying to teach you, then it's no longer for me just oh, here's the full thing, here's the solution.
Okay.
And half of the time my reasoning is just not very good anyways. So these, I think that neurosymbolic AI, it's interesting. It's a very good area of research. It's just a question of we haven't really seen huge successes there yet. So
Okay, with this, the last question. Uh, During your PhD at University of Toronto, you worked closely with uh, Dr. Hinton. What are some of the most valuable lessons you learned from him and that still shape your approach to research today, along with any guidance that you would like to give the undergraduates over here?
yeah, it's a very good question. I think that Jeff was one of the best sort of advisors. I mean, he probably was the best advisor. My time as a PhD student was amazing. I think Jeff, he's one of the things that Jeff did is he's incredibly smart. One of the things that he was able to do is he was able to see past math equations. So his approach wasn't like, hey, here's the objective function that we're trying to do, here's like what we should do. He was also sometimes thinking through the equations and kind of like trying to kind of like get to the high level and sort of what you could do with this system as opposed to just writing math equations. Right, because when I was growing up, I did my bachelor's in computer science and math, and like I used to kind of like have this like very precise notion of like, okay, if I'm solving the problem, I have to have very precise problem definition, like what I'm doing and everything. But he was somehow able to kind of like shift me a little bit in the direction of like, hey, think past the equations, like what's the goal, how are we trying to solve this problem? Like here's like he would throw some intuitions, and then like, and eventually it would come up with something very precise mathematical. And that's a very unique skill that Jeff has that allowed him to kind of like come up with these sort of brilliant ideas that very hard to come up with just by so I guess my message is kind of explore, and Jeff was also giving us a lot of freedom to explore new things. That's something that was like very it's us as PhD students, we were like thinking of a few problems, we're trying to solve certain problems. He would give us hints on like, hey, you know what, like this doesn't look right, like how about like you explore this piece. And through self-exploration we were able to kind of find interesting problems and such. It was good. I mean, I don't know if I have advice. The advice for the undergrads in particular, for those of you who want to go into masters and PhDs, I think learn AI, learn what's happening in AI right now. I think a really great way is to look at the research, what's happening in the research, like the conferences that people are publishing, and a lot of times if you do have a way of doing some research as an undergrad, I think that's super valuable. Picking a particular project and trying to improve, trying to and also being hands-on. Like, don't be afraid. Like a lot of times I do see students basically would say, oh, like mathematically I can write it down, I can't solve it. It's like, I remember this one experience on my side, which was sort of sits with me just very quickly. I've mentioned is that early on, we were training these deep neural networks with stochastic gradient descent, right? And I remember I was talking to an optimization theory person, and he told me, look, deep neural networks, if you have more than a few layers, there's exponentially many local optimum. It's not a convex optimization problem. I can prove to you that it's impossible to train these deep neural networks mathematically, because there's exponentially many local optima. You can never find the global optima. I can mathematically prove to you you can't optimize these models. A student and you're working on some problem, and somebody tells you I can mathematically prove to you it's impossible. Your first reaction is like, okay, well, I don't work on it. But it turned out that it's not true. it is true. It was true in both cases that there are exponentially many local optima. It just turns out with bigger models and with more data, pretty much all of these local optima are pretty good local optimum, and they're pretty close to the perhaps global
Global
optimum. So even though mathematically it's still correct, you can't solve the problem. Practically, you are solving the problem. So that was sort of my so don't be afraid to kind of like push on something that and doing some research as an undergraduate is, I think, it's extremely valuable.
Okay, so with that, we have hit the time limit. So the time you have allotted to us, and with it,
Well, yeah. Thank you so much for the
yes,
invitation,
sir.
and really appreciate you having me. So
Yeah. On this note, sir, I'm really glad to host you, and we are thankful on behalf of Avesh and IIIT Una and all the students to hear from you. We got to learn a lot from your experiences, from the lecture on AI, autonomous AI and agents was fabulous. I personally learned, got to know a lot of topics that weren't clear to me, and like I learned a lot. And your experience, they will hold
great.
always the foremost value, and they'll be always be together with all the students. So thanks a lot, sir. We are really grateful.
Thank you so much.
Yes.
Thank you.
Okay, with this,
Have a good evening.
okay, sir. Excuse me, sir. I've ended the live, and
No, no, I
um,
was just saying, yeah, thanks again, and yeah.
so may we please upload this session on YouTube so that we can reach a